My name is Dan. I'm a software engineer at the D.E. Shaw Group. I work on the application engineering team. And what I'll be talking to you today about is about authorization, and in particular, the authorization system that we made in-house in the firm. We'll talk a little bit about the role that an authorization system plays, and we'll talk a little bit about some goals that we try to make and try to make sure that our authorization system has, and what we consider when evaluating alternatives. Then I'm going to give a little iPad demo where we're going to recreate the data model that we ultimately decided on and made. And then at the end, we'll have time, hopefully, for some questions. Well, let's talk about authorization and what an authorization server or system does. So let's consider a web application, right? You have a web UI that has a restricted tab. Let's consider what an authorization server does in this picture. So when you get a request for your web UI to access a restricted tab, it goes to your web server, you authenticate, and now your web server has to decide whether or not to serve the content to the requesting user. It can ask a question to an Oracle or an authorization system, whether with an API call or something of this sort, and then it'll get back a true or false, and then it will enforce that. This second part here we call enforcement. The asking of the question is something that's solved by an engine that handles decision. How that web API might enforce it is you get back a 403 unauthorized, or you serve the content. So what we're looking for here is we want to have a centralized system to answer this decision part here. And to reiterate what this looks like is that an application, when it wants to decide if somebody should be able to do a certain thing, it calls out to this Oracle and gets back either a yes or no, and then it is in charge of enforcing it. We just want something to handle that part there that gives you back the Boolean true or false. We can see here at the bottom an example of what that might look like, where you call into a client API, and in this case, we're asking about like admin functionality for a simple role-based access control app. You see we get back a true or false. So let's talk about some of the goals that we wanted to have in a system at our firm. So I'll sort of tell this as a story because I think it's more interesting that way. So originally we had a couple small apps. They weren't all that complicated. But then as we started getting more applications, we started to see a need for a centralized place so that we could ask sort of higher level questions like, what's everything that this person is allowed to do across all of our applications? And what we started noticing was that all of these small authorization systems that we were building across all these different apps were starting to evolve and get very similar functionality. And some common examples of the functionality is the ability to audit permissions. Let's say you're in production and you have a problem. This person can't do something. Try and understand why they can't, or try and understand why somebody can do something. We also started to see that certain authorization systems started investing in being able to analyze changes and see logs of maybe all the changes that happened in the last month, the last 6 months, the last year, to be able to get an understanding of changes. If you assume that it works, you audit all the changes. Ideally, it should still work. Also, as we grew and had more complex applications and more applications, we started to have more complexity needed for authorization systems. We started to have complex permissions and the need for complex policies, while at the same time trying to have like concise policies and to have concise permissions. We want to be able to understand what's going on without too much effort. The other thing we noticed was that our applications, most applications, right, they start simple, and then over time their complexity expands. And maybe you have one overarching permission that later you decide you want to make it more fine and have a bunch of different permissions that represent that same permissions. So we wanted to make sure that stuff like that ends up being easy to do, and we think about that when choosing an authorization system for us to use. Other thing, we have a lot of applications here. We want to be able to explore all the permissions that we have and figure out if a permission that we're using is being used somewhere else. If you have a particularly sensitive permission that's being exposed in a bunch of different applications, you really want them to be using the same logic to decide whether or not. If you don't have the same logic, then you have a security hole here, right? So we wanted to make it easy to explore permissions, find what you're looking for, and then reuse it. in all the different applications. So now that we understood a little bit more of what the requirements and what the goals that we wanted to have, we decided to look and see the authorization systems out there. I'm not going to go into the specifics of any one, but we'll just talk a little bit about some authorization paradigms, would probably be the right word for it. So the first one is role-based access control. We think of what an authorization system means here. It means you're going to pass into it a user and a role. The authorization system is going to have some set of policies, and it's going to figure out if there's a mapping from that user to that role. This is really good for simple applications, right? Like it's very easy to use, very easy to understand. If you have a couple roles, things work really well. But as you get more complexity, maybe you start wanting a hierarchy of roles, or maybe you want to have a permission-centric point of view rather than talking about roles. Then you start to want something a little bit more complicated, something like a relational-based access control system, or something like an attribute-based access control system. So if we talk about like something that's one level higher, I guess in some idea of complexity here, or some idea of expressibility, we can think about a relational-based access control system, which the mental model that I have for this is that we're going to make a directed acyclic graph where we're going to have our users over here. We're going to have the things users can do. We're going to draw edges and add some nodes. And we're going to ask the question, is there some path connecting this user to the thing on the right side? What's really good about this is that you can represent a lot of complexity and a lot of hierarchy by adding new nodes in the middle. But you have two sort of hard things as you end up getting more complex. One is that if you go anywhere in the middle of the graph, it's hard to understand what's around you. It's hard to get a good understanding of all of the relevant nodes from a permission point of view without doing some more complicated algorithms or some connected component algorithm or something more complicated, or maybe like a graph similarity score or something like that. So you end up having a problem sort of like if you're on a page in Wikipedia and you want to understand all the pages near you and understand how far away a certain page is. It gets a little bit hard to understand what's going on. Also, if you want to grant permissions and have permissions along orthogonal axes, you can imagine, let's say we have doors. We want to let people open all the doors in New York or let people open all the doors that are red. This ends up being a little bit hard to represent in terms of a graph. You end up needing a bunch of nodes in the middle or having some idea on top of this. But you can represent hierarchy really well, right? Then we go up the chain a little bit, attribute-based access control. We have a user, we have action, we have your environment, and then we have the resource you're asking about. And all of these have key value pairs, and then we're going to write policies, which are going to be Boolean expressions that are evaluations of all of these key value pairs that evaluate to true, which means they apply or not. Now this ends up being really concise, and you can be really expressive, but at the cost of really offering a lot of flexibility to a user. The cost of doing that is that it gets a little bit harder to make higher level questions about what's going on. And you get a little bit too much flexibility, which maybe makes your UI harder or makes it really complicated to answer these higher level questions like, what's everybody who's able to do a certain thing? If you want to reverse index, you now have to have a smart way to evaluate all these Boolean expressions, and it becomes a little bit more complicated there. But you get really concise policies, and you can grant access along orthogonal dimensions fairly easily, right? You can say like, all the doors that have the color red, Dan is allowed to open, or all the doors that are in the location New York, Dan's allowed to open. So what we really want in our system, or in a system where we have a bunch of different applications of varying complexities, we want to be able to support role-based access control for the very simple cases. We want to have hierarchy from a relational-based access control, and hierarchy in ways that are very natural and make sense. And we want to be able to grant permissions along orthogonal axes, like an attribute-based access control. But we don't want all the power of attribute-based access control, and we don't want to suffer from some of the shortcomings you might have with a complex DAG. So what I'm going to do now is the process of a lot of email chains and a lot of iPad drawings back and forth. So right now I'm just going to give like a really speed run version of, let's say, like a year of email chains and iPad drawings back and forth. We're going to talk about making an authorization system here. We're going to talk about the data model that we ultimately made in Turnstile. So let's consider making an authorization system that is going to answer questions about people being able to eat cheesecake. We like cheesecake, or I like cheesecake a lot. There's a little bit of debate about cheesecake versus ice cream cake, but I'm a firm believer in the cheesecake. So let's try and come up with how we can answer this question and make some rules and try and answer some stuff here. So let's write down 5 rules here, and then we're going to try and answer some questions based on these. So I'm gonna call out the questions, and then people could like shout out yes or no. That would be great. Oops. Oh, we're having a little bit of technical difficulties here. But so some rules that we're going to write. We're going to say that Daniel can eat cheesecake. Let's say that humans can eat pound cake. Let's say that Ben can eat pound cake so long as the pound cake is from New York. Or Eric, so long as it's Friday, can eat log cake as long as that log cake is from New York as well. So let's now try and ask some questions here. So let's get the rules up top, and let's ask some questions. And I'm going to ask them aloud, and then if everybody could shout out yes or no, and then, yeah, it'll be good interactivity. Yeah. Okay, so can Dan eat cheesecake? Yes. Yes, so Dan can eat cheesecake because rule number 1 said that Dan can eat cheesecake. Now, can Dan eat at 10 a.m. on Friday pound cake from London? Yes. Yes, for very similar reasons, right? Dan is a human, humans can eat pound cake. Can Eric eat at 9 a.m. on Monday log cake from London? No, right? Because we can't find a rule that applies here, and we want to deny by default here, right? And Eric can eat so long as it's Friday. He can eat log cake from New York, but we see that our policy here or our rule doesn't apply. Cool. So now that we have expressed things in terms of English, let's try and put some nodes and some edges on a graph, and let's try and reconstruct the system and get some hierarchy and represent things concisely. So, oh, beautiful. So we're going to put our subjects here on the left. We're going to put our resources here on the right. See Dan, Eric, cheesecake, pound cake, log cake. And let's try and draw some policies on this graph. So the simplest policy we can make, or the first policy we can make there, right, is that Daniel can eat cheesecake, right? So now we ask the question, can Dan eat cheesecake? The answer is yes, because we can find this path from Dan over to cheesecake. Now we ask the question, can Eric eat cheesecake? No, there's no path here, right? So now let's try and represent this other policy that we made here, which is that humans can eat pound cake. Well, what we can think of doing here is that now that we have this like graph here, let's try and make a node to represent humans. And then we'll draw some edges from Daniel up to humans, from Eric up to humans. And then we can say humans can eat pound cake. We can create an edge here. Apologies for my penmanship. But now we can ask the question, can Eric eat pound cake? We all answered yes. We can see the policy here and understand more the path or why Eric is able to eat the pound cake. Eric can eat the pound cake because Eric is a human. We said humans can eat the pound cake. We can sort of see here, we can represent the organization here on the left, or some hierarchy of groupings of people, right? And concisely represent these groupings being able to do certain things. Okay, now let's try and represent a policy that might be a little bit more complicated. Let's try and represent the policy, Eric can eat all cakes. So one way we can do this, right, is we can draw an edge from Eric over to each one of the cakes. But this is not as concise as we want to be, right? Ideally, we would just want to have one edge. So what can we do? Let's make a node on the right, call it cakes. And now we have some hierarchy of the resources here. And then we can represent this idea here that Eric can eat cakes. by making an edge from Eric over to cakes. Now we can ask the question, can Eric eat log cake? We see the answer is yes, because there's this edge from Eric over to log cake. Now, at this point, we have a DAG, right? We can imagine making more nodes on the left, imagine making more nodes on the right. So let's try and now simplify things, because maybe we don't need all of the flexibility of a DAG, and we want to be able to understand each node and where we are and what all the hierarchy is relevant to a node by looking at that node, right? So what we're going to say is we're going to say, let's say that our resources here have to be a tree. And let's call the node that is the highest level here of our tree underscore. So now when we look at any given node, we can uniquely describe it by its path. And it's relatively easy to navigate through and easy to understand where you are. Kind of like if you're in a file system and you pick any given file, you can walk up the file tree and understand what's going on a little more. Cool. So now we have a little bit of a more complicated system here. We have hierarchy on the left. We have a restricted form of hierarchy on the right. Let's try and represent some orthogonal planes here, right? Let's try and represent that Eric can eat log cake on Friday. So what can we do? Well, what we can think of this doing as well is putting a restriction on when this edge can be used, right? We have resources on the right. Let's try and restrict when this edge is used. So we can say, when? Well, Eric can eat cheesecake when the day of week is Friday, right? Now we can think of asking the question, can Eric eat log cake? And the answer would be yes, only if it's Friday, right? If it turns out to be Wednesday, then the answer is false here, right? Okay, so now we have some restrictions here on when. Let's try and come up with a specification of orthogonal dimensions on our resources. So let's try and come up with a representation of resources that are from New York or from London. So one way we can think of doing this, right, is under each one of our nodes, make a node called like London and New York, right, and make edges here. Do the same. This is visible, wonderful. London or New York. Right, we can imagine doing the same thing here. But, so now we can easily represent, right, that Eric can eat cakes from London. But how do we represent that Eric can eat all the cakes that are from London? Now things get a little bit more complicated as well, right? Like we can think of a way to do this might be to add a new node here, call it London, but then how does this link down, right? It's a little bit hard to know how to do that. So what we can do instead, right, is we can think that this is really a truly orthogonal plane, right? This is an orthogonal dimension in which we want to grant things. So let's make a new tree. And let's say, I want you to, instead of pick one thing from this main tree, let's pick one thing from this main tree and something from a second tree. So for the, that's all good. I'll just erase it here. So for the sake of time, I'll just pull over a tree that I made here previously. But we can pull over this from tree here. Oh, can we zoom out a little bit? I want to make it easy to see. Oh, and now what we can say, right, is that when we ask about being able to eat a certain, or being able to eat cakes that are from a place, we can add a restriction here on our edges and say, well, which one are we talking about here? Well, we're talking about cake that is from New York. We could see now that we have a sort of a reference here to the second tree. When we ask the question, we need to make sure that we specify where the cake is from so that we can get the correct answer here. And actually, we can represent day of week in the same way and have a whole second tree for our day of week too, which I'll pull over as well. It's not nearly as interesting as from, but we can have a day of week tree here as well and include it in the same way. So that is at a high glance how you could construct Turnstile, or the data model that we made from starting from really just English and trying to translate this a little bit easier in a way that still allows us to represent hierarchy. So what's a little summary of what we did there, right? So we started with a bipartite matching problem, which just means we had things on the left, or we had people on the left, things on the right. We talked about matching them together, and then we slowly built up structure on the left to represent your organization or represent groupings of things that you might want to have. And we had structure on the right so that you can organize things and express policies in more concise ways. We talked about using multiple trees instead of one tree so that you can grant permissions along orthogonal planes in a way that lets your policies be pretty concise and lets your permissions be concise. And instead of representing like the cross product in nodes, you can instead pick from 2 trees and it'll be much smaller. We also talked about using trees to allow for hierarchical resources and make things navigable like a file system, make it easy to understand where you are at any given time. This is sort of the main gist of the data model we came up with. So let's talk briefly about the architecture of the system that we made, talk a little bit how we made it, or how we designed it in such a way that it can be scalable and support different needs at different times. So what we had is, or what we have is we have a source or a source of truth for our nodes and a source of truth for our edges, which is our database. And what we do then is we think of making a bunch of different caching instances where people can send requests to that are going to ask requests to a in-memory database, to an in-memory graph database, so that we can get really fast answers, and we can ask and we can ask questions that are pretty complex graph queries. So we now have in each one of these caching instances, we have an API that users can ask questions to that will translate the questions to go against our in-memory representation of our policies and our resources and transform these questions into graph traversal questions, sort of like the ones that we made, or exactly the ones that we asked in this iPad thing we just did. We also have this extra part called the brain, which we need to know which identities we're going to use. And in particular, the source of identities that we use is Active Directory. So we need to sync those identities onto our graph so that we can make the edges that we need to them and make sure that when people ask about the right person, we actually refer to them. So what's next for this system and Turnstile at our firm? So as we have supported more applications, we've had a need to scale more. So there's just some general things we have to do to scale to support more nodes, to support more edges. We right now, when a user wants to be requested to be added to a group, we have primary and secondary approvers based on each group. And what you would ideally want, right, is that when somebody asks to be added to a group, you want to decide if they're able to be added to that group based on the permissions that granting them would entail. Working on that, and to subscribe to updates for a given application. This might be useful if you think of using a centralized authorization system as a policy source for systems that have their own authorization systems, like a secret manager or sudo. You could imagine storing the policies in the centralized system so that you can ask higher level questions about the things that people can do and get change logs, permission paths, but still integrated into other parts of your system. This was, although I'm here presenting this was really the work of a lot of different people across, this was really a collaboration between the trading team, people on QTE, UI engineers, backend engineers. Many of these people are in the Bangalore office, and although I'm here presenting, this is really the work of all of us together. Thank you all for coming.